So here's another Veritasium video where they're trying to pull on the bottom of a bicycle, the pedal, and see if it goes backwards or forwards. My contention is that it's usually backwards, but can be forwards depending on the gear ratio. So things that are going to matter are the distance of the pedal to here, that radius, the radius of the tire, the size of the sprocket here on the crank, and the size of the sprocket on the back of the wheel. I realize I drew it the reverse of the order that's on the picture, so I have the tire in the front, but that's fine. I view it as two relevant external forces, the pulling force and the friction with the road, and internal force of the top tension and the bottom tension of the chain. These two usually aren't the same. I think the friction always has to be forward because it's opposing you trying to pull it. I get the result as if you're treating it like a system, so there's an external applied pulling force. There's sort of an effective mass of the system, which is the mass of the actual bicycle and everything. And then if you take the moment of inertia of the tires and throw in the moment of inertia of the crank, divided by the radius of the tire squared, so it's sort of like a fraction of the moment of inertia, or rather a fraction of the mass because of the moment of inertia, you're going to get some acceleration. That's like F net over m. And that fraction can be positive or negative. So positive acceleration is going to be as if the bicycle is rolling away from you, and negative acceleration is going to be as if it's rolling towards you. So I get this. So it's the ratio of how far is your pedal from the axis of the crank to the radius of the tire divided by the gear ratio. So the gear ratio would be the size of the sprocket on the crank to the size of the sprocket on the tire. I don't actually know that much about bicycles, but generally the sprocket on the crank is usually bigger to make it easier to pedal. So that's why I think almost any time you actually try this experiment, it's going to move towards you unless you cheat and maybe use something to extend the length of the pedal, which I've seen at least one person do. So like here's a Desmos I threw together using this relationship, and this is the gear ratio. Right now I have the pedal ratio set at 0.75, and you can see right there when the gear ratio is also 0.75 or greater, then you're going to get a negative acceleration. This is what you almost always get with an actual bicycle, near as I can tell. But if you were to say extend the pedal with a stick or something, like this would be a pedal that sticks down 10 times farther than the tire. Good luck with that. You would get a positive acceleration, and the bike would move away from you. I don't want to take too long going over this. The PDF is in the description. But here are the four radii that we talked about. I'm taking the positive rotation to be away from the puller. So the friction is going to be forwards, opposing the pulling force. The purples are the internal forces, which is the top and the bottom tension. The external is the pulling force and the friction force. First, I would do net torque on the tire. Then I would do net torque on the pedal, or kind of like the sprocket wheel, whatever you want to call that. I took the definition of a gear ratio, which is sort of the radius of the sprocket on the pedal to the radius of the sprocket on the tire. I expressed the angular acceleration of the pedal in terms of the angular acceleration of the tire, so I can eliminate that. So I put equations 3 and 2 together. Then I added equation 4 to equation 1 to get equation 5, which is just in terms of the angular acceleration of the tire. And then on the next row, because there's no slipping, we can say that the linear acceleration is the same as the angular angular acceleration is the same as the linear acceleration over the r of the tire. F net equals ma in the linear direction. Again, I know it feels weird, but friction's pushing in the positive direction. You're pulling in the negative direction towards you. Rearrange that, substitute 7 into 6. Move things around. I'm actually going to divide both sides by the radius of the tire. That eliminates that, and you get this over r squared. I found over the years it's useful to express moment of inertia over r squared because it's kind of like mass. And you rearrange some stuff, and it's almost like you've got a system here where you're applying an external force from the puller divided by sort of like an effective mass, the actual mass plus that 2 moment of inertias over the radius of the tire squared equals, and then this you quickly realize that, well, wait a minute, big R over big R. That's like the radius of the pedal to the radius of the tire, or what we'll call the pedal ratio. And radius of the tire to radius of the pulley, that's like the inverse of a gear ratio. So when you put that together, you get sort of our final result, where the acceleration of the system can be positive or negative. It's going to be a positive acceleration anytime the pedal ratio is bigger than the gear ratio, which is rare, I think. And it's usually going to be negative because the gear ratio is bigger than the pedal ratio. We're also assuming there's no slipping, and I think this will be the case anytime you're not pulling harder than mu mg, where m is the mass of the bicycle with everything in it. So I don't know. Anyway,